In this video, we're going to learn about oxidation numbers, which can also be referred to as oxidation states. So oxidation numbers are numbers which are used to keep track of how many electrons are lost or gained by each atom. So you should know what oxidation numbers are. An oxidation number represents the oxidation state of an atom or an ion. The oxidation state is the real or apparent charge of an atom or ion. Sometimes the oxidation states are obvious, such as an oxidation state of an ion, but special rules have been developed to determine the oxidation states of atoms in less obvious cases. Okay, so you're going to want to know all of these rules for determining oxidation numbers. Okay, so with these first two, they're just in regards to atoms or ions, which are by themselves. Okay, so all pure elements have an oxidation number of 0. So for example, magnesium by itself has an oxidation state of 0, or sulfur by itself also has an oxidation state of 0. Rule number 2, all simple ions have an oxidation number of the charge of that ion. So magnesium 2+ has an oxidation state of 2+. Oxide ions, which have a 2- charge, will have an oxidation state of -2. Okay. Now, the rest of these rules are going to apply to polyatomic ions or compounds in general. So let's write that out. All right, so the oxidation number of the alkali metals in any compound is +1. Okay, so alkali metals, those are your group 1 metals. So group 1, what I mean by that is we're referring to the number of the column at the very top of the periodic table. So this would include lithium, sodium, potassium, rubidium, cesium, and francium. Okay, the reason why I'm not including hydrogen here is because hydrogen does have some exceptions. Usually it's +1, but there are some exceptions where hydrogen's oxidation state is -1 instead. But we'll get to that in a little bit. Okay, so alkali metals, that is group 1. Okay, maybe let's just go in and highlight the important words here. So pure elements have an oxidation number of 0. Simple ions have an oxidation number of the charge on the ion. Okay, alkali metals, oxidation number is +1. Oxidation number of alkaline earth metals is +2. Okay, so alkaline earth metals, those are your group 2 elements. So if I look at my periodic table, group 2, let's erase this. Group 2 is right here, so that's going to include beryllium, magnesium, calcium, strontium, barium, and radium. The oxidation number for oxygen in compounds is almost always -2, but there are exceptions, like in peroxides, oxygen is going to have an oxidation number of -1. Okay, so an example of a peroxide that's very common would be hydrogen peroxide. Okay, so the oxidation number for oxygen is -1 there. Okay, so each oxygen in hydrogen peroxide has an oxidation state or an oxidation number of -1 in hydrogen peroxide. The oxidation number for hydrogen, so this is what we were talking about earlier, in compounds is almost always +1. However, the exception is going to be metallic hydrides. So sodium hydride, calcium hydride, barium hydride, hydrogen is going to have an oxidation state of -1. So how you identify a metallic hydride is it's going to be hydrogen with a metal. The metal will come first, and hydrogen will come, or the hydride, I should say, will come second. Okay. Rule number 7, when nonmetals combine in a molecular compound, the atom with the greater electronegativity will have an oxidation number equal to the charge of the ion provided on the periodic table. To decide on the oxidation number of the other nonmetal atom, we got to refer to rule number 8. And rule number 8 is that all other oxidation numbers are assigned so that the sum of the oxidation number equals the net charge on the molecule or complex ions. Okay, so with rule number 7 and 8, the easiest way to go about those is just to start with what you know for sure. And leave the unknowns till last. Usually there's only one unknown. Okay, so what you know for sure, that's going to be rules 1 through 6. Okay, always start with those. Okay, so your pure elements, your simple ions, your alkali metals, alkaline earth metals, oxygen and hydrogen, always start with those. Okay, so let's get into some examples here. So we're asked to give the oxidation number of each of the underlying species. So in sulfuric acid here, we just have to figure out, okay, what is the oxidation state of sulfur here. Okay, so I'm going to start off with what I know for sure, okay, because we've got lots going on here. Okay, so for hydrogen, since this isn't a metallic hydride, each hydrogen is going to have an oxidation state of +1, but since there's 2 of them, I'm going to multiply it by 2, so in total, the oxidation number coming from hydrogen is going to be +2. Okay, with oxygen, since this isn't a peroxide, that means that each one of these oxygens are going to have a -2 oxidation state, and since there's 4 of them, the total oxidation state coming from the oxygens here is going to be -8. Okay, so let's just use this information here just to figure out what the oxidation state of sulfur is. So I'm going to use the oxidation number from hydrogen just to start off with, just because hydrogen comes first, and then I'm going to go plus the oxidation state of sulfur. So I'm just going to represent that with X, and since there's only one sulfur, that means I'm only going to represent it with 1X. Okay, and then the oxidation state of oxygen, the total is -8. And then we're going to set this to equal the charge of the overall compound there. Okay, so since there is no number in the superscript position here after the compound, that means this is a neutral compound. So I'm going to go is equal to 0 to represent that. So now at this point, we just have to do a little bit of algebra. So 2 minus 8, that's going to give us -6, and then I'm going to add the 6 over. And this is telling me that the oxidation state of sulfur is +6. So oxidation state and oxidation number are talking about the same thing. Okay, moving on to the nitrate ions. Okay, so once again, we're starting out with what we know. So we don't know nitrogen, but we do know that oxide ions, each one of those are having an oxidation state of -2. There's 3 of them, so that's -6. Okay, so there's only one nitrogen, so I'm representing that with a 1x. Okay, minus 6 for the oxidation states of oxygen, and I'm setting it to equal the charge of the overall ion, which is -1. So if I isolate for x, that's going to give me +5. So this is the oxidation number of nitrogen here. Okay, just keep in mind that doesn't always mean that the oxidation number of nitrogen is forever and always going to be +5. It depends on if what kind of compound it's in, and just everything else around the nitrogen in that particular compound it's in. Okay. Let's do the same thing for this next compound here. So we got -2 oxidation state because this isn't peroxide. So the total amount coming from the oxygens is -10. And since we have 2 phosphoruses, which we don't know the oxidation state of, I'm going to represent that with a 2x. -10 is equal to, now this is a neutral compound, so I'm going to set it to equal 0. If we add over the 10, and then divide by 2 to isolate the x, the oxidation state for each phosphorus is +5. Okay. For our next one here, we've got calcium iodide. So calcium, because that is one of our alkaline earth metals, so it's in group 2. So to show you, it's right here. That's how we know the oxidation state of it is +2. And since there's only one of them, that's the total oxidation state coming from the calcium. So +2 plus 2x for the iodides, because there's 2 of them, is equal to 0 because it's a neutral compound. So 2x is equal to -2. And then if we divide both sides by 2, we're going to get x is equal to -1. So that's the oxidation number for each of those iodides. Okay. And then let's do the same thing for the phosphate ion. So each Oxygen has an oxidation state of -2 because this isn't a peroxide. There's 4 of them, so that's -8. Phosphorus, we don't know the oxidation state of it. Now remember, even though we did phosphorus here, that doesn't always automatically assume, or we shouldn't automatically assume that the oxidation state is 5. It really just kind of depends on everything else around it. Okay, so -8, and then we're going to set that, so this -8 is from the oxygen, and we're going to set it to equal the charge, so that's -3, so +8, so X is equal to +5, so that's the oxidation state of phosphorus in phosphate. And then last but not least, we have -2 times 3 for the oxides, which is -6. So X representing the oxidation state of carbon, -6, and we're going to set it to equal the charge, which is -2. So let's isolate for X by adding 6 over. So X is going to be equal to +4. So the oxidation number, or the oxidation state, for carbon in this compound is +4. Okay, so here's just some practice questions, but I want to move on to the next section here that talks about oxidation numbers. So we can use oxidation numbers to identify oxidation or reduction reactions and indicate the number of electrons lost or gained in situations that might otherwise be difficult. So these situations could be incomplete or unbalanced half reactions, or reactions just where there is no charges. We can also use oxidation numbers for identifying redox reactions and balancing equations. If oxidation numbers change from reactants to products, then it's going to be a redox reaction. If there is no change, then it's not going to be a redox reaction. So what that means is if there is no change in the oxidation state, then whatever reaction you're looking at that has no change in those oxidation states is not a redox reaction. Okay, so oxidation numbers do have some uses. Okay. So, for example, is the following incomplete reaction an example of oxidation or reduction? Let's just see if the oxidation numbers change. So what we're going to want to focus in on is the oxidation numbers of the element that shows up both in the reactant and product side. We're not going to get into balancing chemical reactions with oxidation numbers here. So what we're going to do is we're going to assign oxidation numbers and look to see if oxidation numbers for any of the atoms has changed. So looking here, okay, we know that oxygen is always going to have an oxidation number of -2. There's 4 of them, so that's a total of -8. We don't know what carbon is, so we got to figure it out just really quick off to the side here. So I'm going 2x to represent the carbon, so there's 2 of them, that's why there's 2x. And then for the oxygens, the oxidation state of all of them together is -8. And I'm going to set it to equal the charge, so that's -2. So isolating for x, I'm going to add the 8 over. And then divide each side by 2. So the oxidation state of carbon is 3. So that's each of those carbons has an oxidation state of 3. Okay. Now, meanwhile, let's check out the oxidation state of carbon on the product side. So we got to start with what we know first, which is the hydrogen. Now, hydrogen does come second here, which might make you think that it is a hydride, but because it's not with a metal, so carbon is not a metal, that's why hydrogen is not going to be -1, because this isn't a metallic hydride. So each one of these hydrogens has an oxidation number of +1. There's 4 of them in total, so that means +4. Okay, so if we figure out the oxidation state for carbon here, there's an X representing carbon, +4 from the hydrogens, and then set it to equal the charge of the compound. Since this compound is neutral, it's going to be equal to 0. Subtract the 4 over, and X is equal to -4. Okay, so what's happening here is carbon's oxidation number, also known as oxidation state, goes from this +3 that it was on the reactant side to -4 on the product side. Okay, so what does that tell us about carbon? Well, in order to get from 3 to -4, obviously you need to get more negative. How you're going to get more negative, let's just write Leo, the line goes grr. How you're going to get more negative is if you gain electrons, and gaining electrons is reduction, so that means that this is a reduction reaction. Okay, so these questions underneath for question number 51 are asking you to do the exact same process. So you're going to figure out the oxidation state for the element that you don't know, and then figure it out on the reactant as well as the product side, compare the two oxidation numbers, and then use that to decide if the reaction is an oxidation reaction or a reduction reaction. So just as a reminder here that losing electrons is oxidation and gaining electrons is reduction.